Hello and welcome to our session for today, Grade 12 Physical Sciences. My name is Themba Ncube. Our focus today will be basically on vertical projectile motion, which is part of the physics paper, paper 1. It will definitely be question 3. Right. Just to highlight a few things regarding this topic of vertical projectile motion, it's important to note that the mechanics is a broader, knowledge area in the physics paper, which is paper 1, would carry at most 63 marks. So the 63 marks include all the mechanics, that's your work, energy, and power, your Newton's laws. But for the purpose of today's session, we shall only confine our focus to vertical projectile motion. Right, let's quickly look at the lesson objectives for today. Right, what is it that we want to achieve by the end of today's lesson? Number one, by the end of the lesson, we must be able to define two very important terms, which is free fall as well as projectile. In other words, what that simply means is that as far as definitions are concerned, one of the two terms may be asked, at the end of the year. So in terms of the definition, these are our quick wins. These are our easy marks. Each and every one of us must be able to pick them up, right? And also, we shall focus on describing the motion of a free-falling object or a free-falling body, right? So our motion will be basically based on free fall, right? Now, the description of free-falling objects will be based on the following scenarios. Well, first of all, we'll look at an object that is dropped or released, right? Take note of the terminology there. And then secondly, we'll look at objects that are thrown vertically upwards, right? And then thirdly, we'll also look at a scenario where an object is thrown vertically upwards, right? And from a point that's above the ground, and that object is caught at the point of projection, right? And then ultimately, we shall use equations of motion, right, to determine the position, velocity, displacement of an object at any given time. Any given time, very, very key, right? Okay, just to get us started, as far as mechanics is concerned, which is our vertical projectile motion, there is stuff that we've already covered in our earlier grades, that's your grade 10 and 11, and we just want to try and bring a better understanding of how this all comes together or how it culminates to, our vertical projectile motion. Right, in grade 10, we looked at classification of physical quantities, and we categorize them as far as vectors and scalars. So what is important between these two is that in projectile motion, most of the physical quantities that we deal with, they are basically vectors, and the time being the only one which is a scalar. And also in grade 10, we also managed to describe horizontal uniform linear motion in terms of very two important types of motion, which is uniform motion in terms of constant velocity as well as constant acceleration. Now that says already, we need also to remind ourselves of the concepts that are involved in motion when we talk about position, in terms of where an object is in space relative to a point. And then we also talk about how position changes as the object is in motion. So in grade 10, our focus was purely on, horizontal linear motion. But for today, our focus will only be on vertical motion, right? In grade 10, we also dealt with a lot on graphs of motion, right? We, in many ways, graphs, they also serve the purpose of describing the motion. Very, very important. Because what a graph essentially does, it tells a story of how an object moves or how it changes its position. And by analyzing that motion, we can present the very same motion in terms of the graphs, right? And also, in grade 11, very, very key, we looked at Newton's second law, right? What's so special about the Newton's second law? Beyond just us reciting or stating the Newton's law, we need that very important conceptual understanding of what exactly the Newton's law entails. Remember, what is important to us is that there is a net force, and then the net force causes the object to accelerate. So the acceleration is a consequence of the net force. So if there's no net force, the object stays there. or it moves at a constant velocity. That's how we distinguish between the first and the second law. But for the purpose of today's vertical projectile motion, we shall talk about an object that accelerates as a result of a non-zero net force. Keep that in mind. Right. Let's move on to the key terminology that we want to focus on. As I've already indicated from the inception that, definitions, they form, a critical component of our syllabus. If you analyze the number of definitions that are asked in any typical exam, every long questions will start with a definition. So these definitions are a very important part of our easy marks, right? So free fall is the first concept that we want to look at. Maybe our today's lesson is entirely based on this type of motion. So free fall is the type of motion, very, very important, in which the gravitational force is the only force acting on the object. Now, let's understand this. This is a type of motion. In this type of motion, the object which is concerned is moving under the influence of gravitational force only. Mind you, I'm saying gravitational force. We don't say gravity because those are two, related concepts, but they're not necessarily the same. So we talk about the gravitational force. Remember, in grade 11, we also describe forces in terms of the key words by, on. So when we talk about the gravitational force, we're talking about the force exerted on an object by the center of the Earth towards the center of the object. So the gravitational force is as a result of this phenomenon of universal gravitation. So that's how all these concepts of Newton's laws come together, right? Now, we also want to look at what a projectile is. A projectile, key thing, it's an object upon which the only force acting on it is the gravitational force. So now there is a lot of similarities here, in the sense that when we talk about free fall, we're talking about the type of motion. Yet when we describe a projectile, we talk about an object that undergoes a specific type of motion. So to just put these two together, we are simply saying, the long and short of it, we are saying that a projectile is an object which undergoes free fall, free fall is a type of motion. Very, very key, right? So that's the main point that we want to drive home. And then finally, we're also saying the definitions are quick wins. Keywords are very key, are very important, as it suggests. Now, if you remember very well, the examination guideline is a very important tool for us because we use quite a lot of sources, but the exam guide gives us the precise definitions as per the expectation of the examiners. So if we familiarize ourselves with that document, I think it will go a long way in terms of our quick wins. So the keywords must be used in the correct scientific context. And remember, when we say it's all or nothing, it simply means that it's either you get 2 out of 2 or 0 out of 2. So our definitions must be very, very intact, right? Okay, now let's look at the concept of free fall. I've already indicated the fact that when we talk about vertical projectile motion, in many cases, free fall is the main concept, right? Now, a free body diagram, something which comes from grade 11, it shows the forces acting on an object, okay? So if you check, the definition of free fall says it's the type of motion in which the object, the only force acting on the object is the gravitational force. So if we were to draw a free body diagram of a free-falling object, we would have something of this sort, okay? Now, if we can draw our attention to the free body diagram, you do realize that there's only one force acting on the object, and that force is the force of gravity. Alternatively, we can refer to it as the gravitational force or the weight. This force is on the object downwards towards the center of the Earth, I would assume. So if the number of marks in a free body diagram, from what we already know, it's 1, it means there's only one force. If there's 3, similarly, we'd have 3 forces acting on the object. Right. Now, how do we tell that an object is in free fall under normal circumstances? The phrase, ignore effects of air friction, it says to us, we need to be very, very mindful of that. If we choose to ignore the effects of air friction, it certainly means, yes, friction does exist in real life when an object is falling, from whatever height towards, the surface of the Earth. So if we ignore the friction, it means then by implication, the only force that acts on that particular object is the gravitational force. And then for that reason, the object is undergoing free fall, okay? Right. Now, the only force acting is gravitational force. So take note, that's the symbol Fg, okay? It's different from G. We have met these two, forces before. Rather, I'm talking about the notations, force of gravity and small letter g. Because already we'll be tempted, because there's many versions of g, if we can quickly look into that. This one has to do with the universal law of gravitation, which is the constant, okay, between two objects that attract each other. And then that's the acceleration due to gravity, which is the acceleration of 9.8 meters per second squared. And then this is the force of gravity. Okay, so we must be able to distinguish between those three. So when we talk about the force, so that is the force, that's the acceleration, that's the universal gravitational constant, because there is quite a lot of, legally just mistakes that we commit as far as, the labels are concerned. So we need to keep that well in check, right? And then let's look at the Newton's law, how it fits into the bigger scheme of things. The Newton's second law of motion explains the effect of a net force, okay? So this net force, as a consequence of it acting on an object, it will cause the object to accelerate, right? So acceleration is a result of the net force acting on an object. So this is what we already know. Let's delve deeper into the detail and see how it has to do with falling objects, right? Now, the general description of any free-falling object, whether that object is going up or down, it matters less to us, as long as it is moving on a vertical plane. Let's first of all consider a case where the object moves vertically downwards, under the influence of gravity only, because we are saying the object is free-falling. So our attention is purely on free fall, right? So if an object is to move vertically downwards under the influence of gravity only, the velocity will definitely change. So once there is a change in velocity, then the object is accelerating. Because by definition from grade 10, we understand that the acceleration is the rate of change of velocity. Once there is a change in velocity over a given time interval, then that object is undergoing acceleration. So what are we saying? If the object moves downwards, the velocity, which is a vector, is also downwards. The direction of this vector, which is velocity, is downwards. Now, how is the velocity changing? Is it increasing? Is it moving faster and faster? Those are the simple questions that we want to ask ourselves. So if it moves vertically downward, we're saying it is speeding up in terms of increasing the velocity. Then the direction of acceleration is the same as the direction of velocity, which is downwards. Very, very important. So an object that moves vertically downwards under the influence of gravity only will speed up. It means it will move faster and faster. So the direction of acceleration is downwards as well as that of velocity. Very, very important in terms of our free fall. And then secondly, let's look at an object that moves vertically upward. Let's create a scenario. You throw an object vertically upwards. What happens is once the object leaves the hand, there's no more applied force that acts on the object. Simply means that then only gravity acts on that object, meaning the object is indeed experiencing free fall, right? Now, how does the velocity change? The direction of velocity is upwards because the direction of motion is also upwards. Now, as it moves upwards, it moves slower and slower. That's why we are saying the change in velocity is slowing down, okay? And then the direction of acceleration is opposite to that of velocity because it's moving upwards, yet the acceleration is downwards. So these two have got opposite directions, right? Okay? Let's look at the typical scenarios as we had highlighted in our objectives. Now let's look at the first scenario. We consider an object. It could be a ball, it could be anything, a stone, an object that is dropped or released. So when you drop or release, literally you're holding on to an object, then you let go. Neither do you exert a force on it. You let go and gravity does the rest, okay? So this object is dropped or released from some height above the ground. Then we choose to ignore air friction, right? So the moment we say ignore friction, okay? What does that mean? It means this object is undergoing free fall because gravity is the only force that acts on the object, right? Now, Gravitational force is the only force, which means Fg is the net force. Now, if we go to our, our free body diagram, this is the object under consideration. We represent it as a dot. We know that from grade 11, and then that's our force of gravity, right? Now, gravity is the only force. In other words, the total number of forces or the total magnitude of the force is just Fg. So this means that this force of gravity is the net force. In which direction is the net force? Net force is downwards, okay? So the net force acting on the object is downwards, okay? So if the net force is downwards, what's the direction of acceleration? Because according to Newton's second law, if the direction of acceleration, if the direction of net force is downwards, so that's F net, okay? And then also, our acceleration must be in the direction of the net force, okay? So this object is definitely going to accelerate in the direction of Fg, which is definitely downwards, okay? Right, very, very important point. So the faster and faster it moves downwards, it is because it is accelerating in the direction of Fg. But this acceleration is uniform acceleration, which takes us back to what we dealt with as far as grade 11 concepts are concerned and grade 10 as well. Right, if we're talking about uniform acceleration, we are basically saying that the velocity changes by a same magnitude for every 1 second interval. So per unit time, the velocity will change by the same amount, because basically what we are saying that acceleration is change in velocity per unit time. So if our acceleration is 9.8 meters per second squared, it means the change in velocity is going to be 9.8 meters per second for every second, right? Meaning that if this is the uniform or the constant acceleration, it is due to the constant net force that acts on the object, right? Okay? Now, this is the trajectory or the sketch, okay? I think maybe it could be a new term, trajectory. In some cases, actually in most cases, you may be given a statement that describes a scenario. So the language, is very important. We highlight the keywords so that we can get a better understanding of the scenario. But in addition to that, it's also important for us to kind of, just make a rough sketch to better analyze the scenario. So that's what we call a trajectory. So this object, let's say it starts from point A, and then it ends, let's say, on the ground at point B, right? Okay, so those are 2 points in which the object moves. So if it is dropped, this object will start from rest, right? This is not new from grade 10, meaning that the initial velocity of the object is 0 meters per second in the case of units, okay? Right, now if it's moving faster and faster, it means then our acceleration is also constant. Now, faster and faster, it suggests that the final velocity of this object will be maximum, right? Because it's moving faster and faster as we have justified it because it undergoes uniform acceleration, right? So the magnitude of velocity gets bigger and bigger and bigger, depending on how far down it travels. So the trajectory gives us an impression or a better understanding of the scenario as far as what is happening as far as the motion of the object is concerned, right? Okay, right. And then let's look at the second scenario, an object that is thrown vertically downwards, right? How is this different or similar from the previous scenario of just dropping? Now, if you're dropping, you just let go and then gravity does the rest. But in the case of throwing down, we exert a force on the object until the point it leaves your hand. The moment it leaves your hand, that applied force is not existent anymore. Only gravity acts on the object, meaning that in that case, the object is also undergoing free fall, right? But how is this different? It says to us that the initial velocity is no longer going to be 0 in this case. It can be anything except 0 because the object does not start from rest. Okay? So that's the key idea. The object does not start from rest. For that reason, the initial velocity cannot and will not be 0. Right. Let's say, for argument's sake, we throw it down, for argument's sake, at 10 meters per second. Right. What are we saying? And then this object undergoes uniform acceleration. Okay. if the acceleration is uniform and it starts with an initial velocity of 10 meters per second, by implication it says after 1 second, the velocity will change by 9.8, meaning that it's going to be 19.8 meters per second. The direction is still downwards, okay? And then after 2 seconds, it will be, V will be 19.8 plus another 9.8 meters per second, which gives us, I think it's going to be 19 and then plus 10, that's 29.6 meters per second, right? Now, if you check, the magnitude by which the velocity changes remains constant, in this case, which is going to be 9.8 meters per second for every 1 second, okay? So that's basically what is happening as far as an object that is thrown vertically downwards. So key point is that we must consider the object from the moment it leaves the hand, because only gravity acts on the object, which then says the object is free falling indeed, right? Now, the direction of the initial velocity and that of the acceleration is the same, because this object moves downwards and the acceleration is also downwards. Let's look at the third scenario, okay? A little bit different somehow. It says an object is thrown vertically upwards, okay? That's the first part. And then subsequent to that, it returns to the point of projection. And again, we're still ignoring air friction, right? The moment we start ignoring air friction, it says, this is what I always want to emphasize, that the object is free falling, right? And the implication of a free falling object is that it has got a what? A constant acceleration, right? And then that constant acceleration, we need to understand that is that g, which is 9.8 meters per second squared. The direction is downwards. Now, speaking of which, you know, the data sheet becomes a very, very critical and important tool, you know, in our problem solving. Now, if you look at the table 1 in paper 1, right at the end of the question paper, you'll have your data sheet, which shows all the physical constants, which we must be familiar with, right? So g is only but one of them, okay? Now, if we consider the motion of the object, okay, from the instant it leaves the thrower's hand, only gravity acts on the object. We have highlighted that is free fall. Okay, so the object moves slower and slower. Why does it move slower and slower? Let's make a sketch of that. Now, as the object leaves the hand while moving upwards, this force only acts on the object, which is the force of gravity. Okay, now, in which direction is this object going to accelerate? It's going to accelerate downwards according to Newton's second law. But as it moves upwards, it's getting slower, it's moving slower and slower as per that table of summary that we looked at earlier on. So if it's moving slower and slower, it simply means that the initial velocity, in this case, which is upwards, versus the acceleration, which is downwards, are in opposite direction. Very, very important. So as an object is moving slower and slower, going upwards, it is actually accelerating in the opposite direction of motion, in this case, which is vertically downwards, right? Okay, and then as the object slows down while moving upward, it's actually accelerating in the direction of gravitational force, which is downwards, just to reiterate that point. However, the acceleration remains constant, very, very important, right? And then let's look at the trajectory concerned as far as if we were to sketch that motion. So this object, if it slows down going upwards, it's definitely going to speed up going downwards. So that's why we are saying that the velocity initially is maximum. But as it accelerates downwards, what is actually happening? It gets moved slower and slower. How slow can we get? The slowest we can get is that the object will come to rest, okay? So if the object comes to rest, okay, it means that the final velocity at the highest position is going to be 0. Okay, right. Then from that moment, you know, it will momentarily stop, and then what's going to happen? The object will move downwards as if it has been dropped, because it will start with an initial velocity of 0, moving faster and faster downwards, which is why the final velocity, if we consider the motion from the highest point to the point of projection, it says that it will move faster and faster. But I want you to take note of the magnitude and direction of acceleration. The acceleration for upward motion is 9.8 meters per second squared downwards. The acceleration still for the downward motion is 9.8 meters per second squared downward, meaning that this acceleration remains constant, which is why we're saying that the object undergoes constant or uniform acceleration. That's the main idea as far as free-falling objects are concerned. Right. Okay. Now, that said, maybe we also need to look at the language, which forms a very, very important component of our science, because science on its own, it is a language. Then we have got our own terms or terminology, you know, the jargon that is specific to our subjects that we need to, you know, to ask ourselves. You know, if you look at, you know, how long, you know, if say an examiner wants to ask you to calculate the time, sometimes they may say calculate the time, which is very straightforward and direct. But if it says how long, it's an indication that you need to calculate time. The other one could be how fast. How fast is rate, which can be either speed or velocity. Take note that speed becomes a scalar and velocity is a vector. So if they didn't say the magnitude of velocity, we must also include the direction because of the vector nature of that quantity. And then, because we're talking about objects released at some height, sometimes you may be asked how high, you know, with the question mark, refers to the distance or the displacement, which has to do with the change of position between any 2 points of motion, right? Now, if an object is dropped, we've said the other word is released. It means that the object will start with an initial velocity of 0. So if an object, again, is thrown, it implies that the object is given a non-zero initial velocity. It could be either upwards or downwards, right? That said, these are basically not all the, you know, the scenarios that will be pretty much examinable at the end of the year. So, you know, it goes beyond this, but these are just to give us you know, a basic understanding of what exactly freefall entails. So the examinable scenarios will be an object that is dropped from some height. We've looked at that, right? Or it could be an object thrown vertically downwards. We have also looked at the trajectory thereof. And then it could be an object that is thrown vertically upwards, right? Or the examiner may decide to say an object is dropped from a moving object. Now we need to consider relative initial velocity in that case. We'll talk to that at a later stage. And then, you know, at the other end, we could also consider bouncing balls, you know, in a scenario where an object is allowed to hit the floor, bounce, move up and down on a vertical plane, right? Then problem-solving strategies, because this is, you know, physics, you know, in its own right. And there's this general conception that physics is about calculations. No. If you realize, you know, wait a minute, okay, we haven't done any calculations up to thus far. We've just picked to the concept of what exactly freefall is. The moment we can do the science correctly, then the mathematics becomes only natural after that. So our focus is not to carry out a lot of complex calculations, it's to understand why we do the calculations that we do, you know, which is the science. So it's first the science, and then the maths will follow after that. Now, strategy in terms of solving the problems, we must draw the trajectory if necessary, if it's not given, okay? So we must draw that trajectory just to give us a better understanding of the scenario. And then number two, we can also indicate the critical points in a trajectory, point of launch, you know, the maximum height, you know, the point of symmetry, you know, as we have seen with the case where an object was thrown and then caught at the point of projection. This one, very, very important, choose sign convention. This is about vectors. So the only scalar that we dealt with in our discussion in this session was time. Everything else, you know, your position, your velocity, your acceleration are all vectors. So sign convention in terms of direction becomes very important. Now, when applying equations of motion, always consider the motion between any 2 points. So it means when the object starts moving, at that point, it becomes the initial point. And where we choose to analyze the motion up to a certain point, the final point then becomes, you know, the second point becomes the final point. And then we must also take direction into account. Now, the data sheet, very, very important. Here it is. This is the data sheet, which is going to be given. There's no need for us to, you know, memorize all these complex formulas. Or, you know, all we need is to understand which formula to use and when. Now, the data sheet is going to be provided to you. There is no need to try and say, for argument's sake, you want to look at time. You know, you are given velocities and acceleration. There's no need to make time the subject of the formula. Just identify what is given, and then isolate the unknown as a simple linear equation. So the data sheet is something that we need to familiarize ourselves with, right? And then last but not least, just a simple, worked example, just to give us a sense of what exactly this problem solving entails. I think it's also going to give us an idea of how we work on these projectile problems. Here's a scenario. It says a ball is thrown vertically upwards with a speed of 15 meters per second, upwards speed, right? From the edge of a balcony and strikes the ground 6 seconds later. So this object, here is a balcony, is a sketch. So there is the object, it's thrown upwards, okay? It's allowed to go to the ground and reach the ground after a certain time interval. Now, the time for the entire motion, we're told it's 6 seconds, right? Then we ignore friction. The moment we see ignore friction, immediately the concept of free fall comes to mind. So this object is free falling. Okay, right. Now, then it says here, 1.1, as I've indicated earlier on, every long question would definitely have a definition alongside. Now, it says define the term free fall. Now, check the number of marks, okay? It's 2 or nothing. These are our quick wins, the keywords, all or nothing. Now, if we talk about a free-falling object, you know that this is free fall in terms of type of motion. The type, okay, of motion in which the force of gravity, okay, is the only force. I want to emphasize on only force acting on object, okay? Now, I've indicated that the number of marks is 2. Now, we need to capture the keywords correctly, and when I read my definition, this is what you need to do in practice, you should read it over again and check if it makes scientific sense. You may have all the keywords, but are they in the right space, at the right, places to make the correct scientific meaning? So that's the definition as it should appear as far as the exam guide is concerned. And then now, this is our focus for now, which is the calculations. Now, it says calculate how high above the balcony the ball travels. Now, without diving straight into the calculations, there's the issue of, one, the trajectory. We've addressed that. Secondly, we also need to consider the sign convention. In other words, we need to define or choose our direction. For the purpose of this example, let's take upwards as positive. Take upwards as positive, meaning that downwards is negative, okay? So, and as long as it's free fall, our acceleration is always downwards, okay? As long as it's free fall. If upwards is positive, then it means our acceleration will be negative, meaning negative 9.8 meters per second squared. The negative suggests the downwards, okay? And then we want to calculate how high above the balcony the ball travels. Now, we must consider motion between any 2 points so that we are careful, because the 6 seconds is not just for upwards, because the 6 seconds is for the entire motion of the ball from where it was projected until it strikes the ground, okay? Now, if we look at the scenario, we ask ourselves, okay, we're given the time. So this is the time for the entire motion. So I'm going to say, consider motion from the point of projection, okay? To the ground, okay? So that's the entire motion of the ball, right? So it means then our delta t, for that sake, is going to be 6 seconds, okay? Right, what do I have? I'm also told how fast the ball was projected. In which direction was it projected? Upwards. And we said upwards is positive, meaning our initial velocity is equals to positive 15 meters per second. I also want you to note that the direction of acceleration and that of the initial velocity are opposite, meaning that the object is accelerating downwards while moving upwards. Right, now we want to calculate how high. Right, if I can quickly go back to that balcony. You know, they want us to know how high the balcony, or how high above the balcony does the ball travel. How high above the balcony? Wait a minute. Above the balcony, that's what we're talking about. So all this information that we have here is irrelevant because the 6 seconds is not for the movement from the point of projection to the highest position, okay? So we're not going to consider from the point of projection to the ground, you see, because this is the most of the data that we have been given. But we know that if we go back to the trajectory that we drew, we know if we consider motion, let's say this is point A, and then the highest position is point B, okay? And then we consider the motion between A and B. A becomes initial point, B becomes final point. We know that at the highest position, the final velocity is going to be 0, right? We also have the initial velocity at A, which is going to be positive 15 meters per second. So we need to pay careful attention to, you know, the detail as far as the information that is given. So that's our initial, then our final is going to be 0 meters per second, right? We don't have the time. So because we can't use this time is not for the motion from the point of projection to the highest position. So now we've got the final velocity, we've got the initial, we've got the acceleration. We do not have the time. I want to emphasize on that because this time is not for the motion that we are considering. Then we're going to say, okay, which equation can we use, which doesn't have time? That's going to give me, you know, the displacement or the change of position. It's going to be Vf squared is equals to Vi squared plus 2a delta y. Why are we saying delta y? Because this is change of position on a vertical plane, right? Finally, it's 0 squared, okay, is equals to initial, which is 15 squared. Marks are given for the actual substitution, okay, plus 2. But wait a minute, our acceleration is negative because it's downwards, negative 9,8, and then delta y, okay? So this reduces to a simple linear equation that any one of us can do. And you realize that the moment we start doing this, the science we've done already, then we can isolate our unknown, in this case, which is delta y. Your calculator becomes a very important tool there. Then we've got 15 squared, okay, divided by 19.6, okay. Okay, which gives us negative. It's going to be positive because we've transposed that. It's going to be positive 11,48 meters. Right. If you look at that delta y of 11,48, it says if we go back to our trajectory, it means this displacement or this change of position in the upward direction is actually 11,48 meters. Okay, excuse me for that. Right. 11,48 meters. So that's the displacement. Now, the main thing that I want to also drive home is that not all this information that is given here we're going to consider for every question. We need to carefully look at the trajectory, make sense of the trajectory. And then if you look at the number of marks that is given here, it's 3 marks. So if a question is 3 marks, be aware that we're actually saying you have to identify, number 1, the correct formula, okay, without attempting to make the subject of the formula. Number 2, do the correct substitution, okay? And when we talk about correct substitution, we're saying take direction and the vectors into account. And then the final answer, in this case, which has got the correct SI units, okay? So it's very, very important as far as problem solving is concerned, right? And then if you look at the second question, which says the velocity of the ball when it strikes the ground. Now, here's the balcony, there is the ball. It is projected vertically upwards. It goes all the way to the ground. Now, if you check, the time that's given is the 6 seconds. This 6 seconds, if we were to give maybe labels to these key points, if this is A, that's point B, let's say that's point C, and then the ground is point D. Now, the 6 seconds is for the motion A to D, right? Motion A to D. That's the 6 seconds. That's our delta T of 6 seconds. Okay? And then the acceleration, we've already chosen our direction and said if upwards is positive, downwards is going to be negative 9,8 meters per second squared. Right. What else do we have? because we want to calculate the velocity with which it strikes the ground. We were definitely told that it starts moving upwards at 15 meters per second. So this 15 is going to be positive because we're saying upward is positive. What are we looking for? We're looking for the final velocity at which the ball strikes the ground. Okay, right. So from there, learners, this is the science that we're talking about. Okay, what follows after that in terms of, your substitution, the use of the scientific calculator correctly, that is, becomes, the maths. So we first do the science, then the maths will definitely follow after that. Right, okay, just to quickly do that, because we are given, we say final velocity is equals to initial velocity plus a delta t. Because what informed our choice of this equation of motion? Definitely, it's what we have and what we're looking for. We are looking for that, okay? We have that, we have that, we have that. So how many unknowns do we have in this linear equation? It's going to be definitely 1. So the final velocity with which the ball strikes the ground is equals to the initial, which is positive 15, plus 9,8, which is negative. Why? Because this is downwards. Okay, the time we're given is 6 seconds. Then we go to our calculator. It should work to, I think, 43,8. If we can quickly confirm that, then it's going to be 15 plus 9,8 times 6. Okay, it's positive 15 minus 9,8 times 6. It gives us negative 43,8 meters per second. Right. What's the implication of this negative? Let's talk the science behind it. Because as the object is moving, from the highest position all the way down, in which direction is the object when is it moving when it reaches point D? It will definitely be moving downwards. And we say it upwards is positive, and then downwards is going to be negative. So that's the magnitude of velocity as far as the direction. So when they say the velocity, they want both magnitude, okay, and direction. Right. So nobody asked us to calculate VF. Let's answer the question, because the question says calculate the velocity. We can say, therefore, okay, the velocity, okay, of the object is 43,8 meters per second. In which direction? Downwards. Okay. Right. So that's the magnitude as well as the direction. Okay. So that said, this is also a typical, routine calculation with 3 marks. The formula, the substitution, as well as the answer. Then lastly, just to sum it up, we said we were describing the motion, and we agreed that the motion can also be described in terms of graph. Now we want to sketch a velocity versus time graph for the entire motion of the ball. So on the graph, we must indicate the initial velocity, okay? We must also indicate the final velocity. This one we have already calculated. We were given, and then we were also given the time for the entire motion, right? So as far as the graphs are concerned, take note of what is needed or to be included as far as it is concerned. But because of time constraints, definitely maybe in the follow-up sessions we'll have an opportunity to look more into detail. Thank you very much for your time. Hopefully this has been a fruitful session for you. From myself, Themba Ncube, it's cheers and bye-bye for now.